That's all I've got this morning. I'll pass it back on to Randy.
Thanks, Bruce. So one thing that we wanted to do this summer, and then again probably later in the fall as we head to NBM 3.2, is have kind of a series of presentations about the NBM. Now that we've switched over to that as our initial starting point, and then we'll revisit this topic in other areas when we get on to 3.2 later this fall. And so this morning, Andy has invited Eric Engle to speak, and I'll let Andy go ahead. And Eric, I'm going to transfer control over to you to share your screen while Andy introduces you.
So I went out to MDL last September, and I got to speak with Eric. Eric is the NBM technical lead, and he introduced me to the QMD process, one of the, I think, greatest utilities coming out of the NBM. It's a pretty high level process. So I really wanted to let him, who's working with the whole process, doing all the coding, be able to give you an introduction to how the QMD works. So with that, I'm going to pass it on to you, Eric.
Okay, thank you. Can everybody hear me okay?
I can hear you, Eric.
Okay. So, my name is Eric Engle. I am the NBM technical lead in the Statistical Modeling Branch, and hopefully in the next half hour I can show everybody how the quantile mapping and dressing procedure actually works in a visual sense. So, before we get started, the quantile mapping algorithm and a lot of the prototype source code was developed at NOAA OAR by Tom Hamill, and with contributions from Michael Scheuer, which I guess I'm pronouncing that correctly, and a lot of the quantile mapping information can be found in the two journal articles that are being shown on the screen right now. This is kind of a first for MDL, directly taking prototype code from outside and massaging it into an operational framework and getting it running on the supercomputer platforms, and that's been happening now for almost 3 years. So, quantile mapping and dressing. QMD. So, I'm trying to,
That little red arrow down.
This one?
That one.
Okay, I just wanted to clear something off of our screen, I'm sorry. So it utilizes cumulative distribution functions, CDFs, generated from some sort of n days worth of model forecasts and analysis data sets. In this case, our training sample are the previous 60 days worth of model forecasts and analyses. Oh, now I'm back. Where did my mouse go? Uh-oh.
I see it.
You see? There we go. I'll just spacebar. So, in kind of a one-sentence summary, you map the quantile associated with the model forecast at a given location, say a grid IJ grid coordinate, to the analysis and replace the associated analyzed value for that same quantile. The quantile mapping it's a conditional bias correction method upon the forecast amount. When your analysis data set is of a high resolution, it implicitly performs a statistical downscale, and it can and tries to avoid the collapse of spread that's commonly associated with some regression techniques. So in order to do or to perform quantile mapping and dressing, there's a handful of steps that have to take place first. First and foremost, ingest and archive 60 days worth of numerical weather prediction data and precipitation analyses. In the case of the quantile mapping that's in production right now, we're upwards of 160 individual models if you count ensemble members as an individual model, and that's going to jump to about 170 in 3.2. and that's at the shortest. That's at the shortest lead times. As you move out, and lead time models fall off, and you're left with probably close to 60 or 70 towards the very end. Next, you want to interpolate all of your NWP data to a common high-resolution grid. In this case, for precipitation, we use a budget interpolation. Generate forecast CDF per modeling system and an analysis CDF using 60-day training. And then interpolate today's model forecast to the same common high-resolution grid. And in this case, if we're doing precipitation amounts, you would want to use the budget interpolation scheme. So once these processes are done, you now have, sorry, something got messed up. You now have the components necessary to perform the quantile mapping. You have your analysis CDF, which is comprised of your 60 days, in this case of IRMA QPE. The analysis CDFs are also generated using supplemental locations, and I will get to that in a couple of slides. You have your forecast CDF, which is the previous 60 days of, in this case, GFS, interpolated to our product grid, also using supplemental locations. And then you have your model QPF, today's forecast interpolated to the product grid. In a visual sense, that's what those three data sets look like. We have XY axis, X being your precipitation amount and Y being CDF values. The red line, hopefully that's bold enough for everyone viewing. The red line is the GFS forecast CDF. And the blue line is the analysis CDF. And then in the lower right-hand corner, we have our current model precipitation forecast. And I have to go back a few slides. Something got a little screwed up. So our walkthrough scenario is going to be from the GFS from last December, the 0Z run from the 13th at a lead time of 48 hours for CONUS grid point 1937 by 820, and it's the approximate location of the Lancaster, Pennsylvania airport, KLNS. A lot of these slides I reused from a seminar that I gave at Millersville University back in February, but the case, it's also a pretty good synoptic case to take a look at. We have a low pressure system in the southeast. We have what would appear to be maybe a little bit of cold air damming with an inverted ridge along the Appalachians. And in this scenario, precipitation onset is sometimes difficult to forecast. You have a lot of battle versus dry versus moist air, especially in the mid-Atlantic. So that's our scenario for this walkthrough. And that is the raw model forecast amount in the lower right-hand corner, 0.814 millimeters. So that's raw GFS 12-hour precipitation amount for a 48-hour lead time. So the CDF generation, previous 60 days plus supplemental location. So we're going to briefly mention the supplemental location process. So the supplemental locations are used to augment, or in this case, increase the training sample size for CDF generation. So at every grid point can have upwards of 50 locations, 50 other grid point locations with similar climatology and local terrain characteristics. So we have a standalone program that does not run in production. It's in the development cycle, and it performs this process of developing a relationship between a single grid point and every other grid point. This is a very time-intensive program that I had to rewrite in MPI in order to get it work on a 2.5 kilometer grid. The inputs for this program are a monthly precipitation analysis climatology. In this case, we have a 16-year sample to work from. Terrain gradients in the east-west, north-south direction, and distance between grid points. If you throw that together and you weight some of the precipitation differences versus terrain differences versus gradients and distance, we come up with a performance penalty, essentially, and we take the 50 best locations. We also use distance thresholds, so supplemental locations are not clustered together. So for the grid point in question, here are the supplemental locations for the month of December for the grid point approximately for KLNS. The larger black circle that represents the grid point in question, the first supplemental location for that grid point is its own grid point. The smaller black circles are the top 20 grid points, and then the darker gray are I think 20 through 40, and the light gray are the lowest. Like 40th through 49th supplemental locations. So when we develop or generate the forecast and analysis CDFs over 60 days, we are using the following grid points also for our grid point in question, which is the larger black circle. A lot of these make sense. You have some things getting in there. I don't know about this, in Illinois and Indiana. If you tweak a few parameters here and there before running this, you can get a different collection of stations. And once again, every single 2.5 kilometer grid point has a collection of 50. So doing this by month, by grid point, we're trying to figure out ways to figure out, well, what configuration of weighting of precipitation climatology versus terrain is the best for a given area for a given month. So it's a pretty big challenge. Coming back from supplemental locations back to the CDF generation, right now our software has the capability to create two types of CDFs, an empirical one based on 91 non-exceedance thresholds from 0 to all the way out to 1,000 millimeters. That's what is currently used in production and has been since quantile mapping has been implemented. The other type is gamma distributed parameters. That'll be new for 3.2. You can see where the benefit for gamma comes into play. You only have to store 3 parameters, which is the alpha and the beta of the gamma distribution, along with a fraction 0 parameter. So, you're storing 91 values per 2.5 kilometer grid point. In 3.2, we'll be storing 3 parameters. So we're going to be saving a lot of disk space. When you look at these visually and do the work to kind of look at a certain threshold from the gamma parameters, things look pretty similar. So our trade-off here is just preservation of disk space for perhaps future work. During this walkthrough, however, and for the sake of this walkthrough, the CDFs that we're looking at are empirical in this case. So now we're just going to walk, step by step, walk through the actual quantile mapping and dressing procedure. So step 1 is determine the CDF value associated with the model precipitation forecast. So we have our model precipitation forecast in the lower right, 0.814 millimeters. We have our model CDF in red, our analysis CDF in blue. So what we essentially want to find in step 1 is that CDF value along the forecast CDF. So we don't know its value right now. We have to do a little bit of linear interpolation. But because these CDFs are empirical, we have we have CDF values associated with certain precipitation amount thresholds. And we do have CDF values for a 0.8 and a 0.9 millimeter. Those values are shown on the screen. So now we have to get a value for the forecast CDF. So it's simple linear weighting between the CDF value at the threshold below the precipitation value and the threshold above. So if we do all this work, we come up with an interpolated forecast CDF value of 0.7363. So 0.73 essentially. That's our first step. Second step is simply to map that interpolated forecast value onto the analysis CDF. In this case, as we look at this visually, we are just placing where 0.73 lies on the analysis CDF. Now, in code, there's a lot to talk about. Visually speaking, we're just moving that dot from where it lives on the forecast CDF along the y-axis over to the left. Now, moving to the left in this case is not always the case. It just happens to be for this demonstration. So now we have taken that interpolated forecast CDF value and placed it on the analysis CDF. So now we need to determine the analysis precipitation value associated with that mapped CDF. So it's kind of the reverse of step one. Is now we know the CDF value, we have to determine the analysis precipitation value associated with that mapped CDF value. Once again, we do not have a precipitation amount for the 0.7363 CDF value in the analysis CDF, but we do have thresholds for 0.5 and 0.6, and obviously you determine those threshold bins with a big do loop for in Fortran. So we do have at 0.5 and 0.6. So it's very similar to step one. We know the analysis CDF values at those two precipitation amount thresholds. We simply calculate a weight for the upper threshold, and we multiply, and we go 1 minus the weight at the lower threshold, and we arrive at the quantile mapped value of 0.55 millimeters. That is essentially the quantile mapping process. Now, in code form, that's a lot more intense as we work on this at every 2.5 kilometer grid point, and we try to do this in an efficient manner. Step 4 is to now we dress this quantile mapped value with some random amount dependent noise. So after the quantile mapping, sampling error, biases, under dispersion can still exist. So we dress each individual quantile mapped forecast with a random amount dependent noise. We use a random number generator that we seed with the raw model domain average. So the entire two-dimensional GFS grid, we take that average, and that seeds our random number generator. And then we draw from a normal distribution where the mean is 0, and the standard deviation is 0.5 times that quantile mapped forecast value. Now, in the journal articles, and even right now, this is a trial and error type of dressing procedure. We are hoping that future versions have a more objective-based dressing method. That depends on computational factors, mostly. So the summary of the walkthrough is we start off with a raw forecast model of 0.8. It is quantile mapped down to 0.55. we have our standard deviation that we calculate. And then we come to our quantile map and dressed value. That's where the random noise comes in, is we multiply the standard deviation by the random number deviate, which in this case is a negative 1.2 value. So we come out with a quantile mapped value of 0.20 millimeters. That is quantile mapping in a walkthrough for a single model at a single grid point for a single lead time. Now, in production, we are doing this at every grid point for every single model input at every lead time that we provide quantile mapped output for. So how did this verify? You know, it is a statistical downscale. It is a bias correction. How did it verify? So the map is a zoomed in view of IRMA 12-hour QPE, valid for the 15th at 0Z, 48 hours from 13th 0Z. You notice over southeast Pennsylvania, or just over southern Pennsylvania, we have some there. According to IRMA, we have some light precipitation. Over southeastern Pennsylvania, you know, there is getting towards south central Pennsylvania, there is a little area of heavier or larger accumulation. So the IRMA QP at that grid point was 2.6 millimeters. So you know, we definitely, you know, verifying against IRMA, we were under that by a couple millimeters. If you take a look at the observations for KLNS in the 12-hour period ending at the 15th 0Z, you can see that they recorded no precipitation. At the 14th 23Z, there's a trace amount, and then at the 15th you get your 1/100th of an inch that would verify a pop forecast. So, you know, there's always the battle versus, you know, gridded verification versus point verification. The grid point in question is very close to the KLNS METAR. I don't know the exact distance, but it's very close. That is the QMD walkthrough, very similar to what, you know, Andy saw at when he visited MDL last year. But I thought this case, you know, as I used it earlier in the year, is still a pretty good case to demonstrate. And that's it. Anyone have any questions?
Yeah, great talk, Eric. And yeah, I think this is an amazing process. You think about have to do this on, for every model, at every grid point, for all the projections. You got to store all this data for 60 days. It's pretty amazing. So yeah, we're going to open it up here to questions. Feel free to raise your hand, and we'll unmute you here.
Phil, we're unmuting you. Go ahead, Phil.
Yeah. Hey, thanks, Randy. Yeah, hi. Thanks, Eric, for the talk. Just so I understand best, so you went through the process for one model, the GFS. So you do this for every model, then you come up with a new CDF, essentially, and then you develop your probabilities from that. Is that correct?
Yeah. So I guess I'll take the first part. Yes, this is done for every model, every 2.5 kilometer grid point. Even, you know, if we're talking about something like the GEFs, which is at a 1/2 degree, we do interpolate down to 2.5 kilometers. It doesn't, it still looks like a 1/2 degree grid, but you know, we get everything on a common grid to do all these processes, you know, at once over, you know, some, you know, large parallelized Fortran program. The CDFs are generated every day. So every day we are taking in, you know, new model data, offloading the oldest, and regenerating CDFs. So this is done at, like I said, at every grid point for every model. For probabilistic product generation, we also use a stenciling technique to, and then I didn't want to go into the product generation side of it, but your question obviously begs that. So we have a 9-point stencil where we use surrounding grid points, the forecast CDF and the forecast value from surrounding grid points, and we quantile map those to the central grid point of the analysis CDF. So what happens when we create a probabilistic product is that going into the quantile mapping process, you have, say, 170 model inputs. Coming out of the quantile mapping process for a probabilistic run, you have 170 times 9 quantile mapped and dressed forecast values, and that brings you up to around 1,500 potential forecast values per grid point. And then from that, to create a pop, we just look at the relative frequency of those 1,500 forecast values that exceed the pop threshold or any other probabilistic threshold. From that, say, vector of 1,500 values, we can also, and we sort that, and then you have your percentiles. And in 3.2, I think we're outputting every percentile from 1 to 99.
Oh, okay. Yeah, that makes sense. I was just curious what that step was that took you from the QP, the quantile QPF from one model to the probabilistic forecast.
Yeah.
So thanks.
Yeah, no problem. That's the thing, and that's, obviously I'm not going to say if your question's valid. There's no such thing as dumb question, but it does beg the question in this walkthrough. Okay, this is essentially a deterministic procedure. We're doing this to individual grid points. Correct. We are bias correcting each individual grid point. The probabilistic nature comes in is when you just combine all of those from all the models, especially, or in the case if you have an ensemble system, you could just compute the probability, the quantile mapped probability for that individual system. That flexibility actually does exist in the software.
Okay. If you don't mind, I have just one last question. Have you noticed if there's big pattern changes, say you go from a dry pattern on the East Coast to a wet pattern, does it struggle to, is it as reliable in those cases, or is it pretty, because of how the process is done, it's able to adapt to those changes in patterns over, from a previous 60-day period to, say, the next 10 days or so? Maybe it goes much wetter.
It does struggle. Just objectively looking at this, it does struggle when there are regime changes. And, a lot of my, replies to like this sort of question that we get kind of in the Blend forum in VLab, a lot of this kind of goes back to the supplemental locations aspect of the CDF generation. That increases your sample, for CDF generation by a factor of 50. So you're hoping that the climatologies of those other grid points are coming into play to inflate the sample size for the CDF generation to perhaps capture something that might exist even though we're having some sort of pattern change. The idea is, we've talked about, can we extend out, 90 days or even 120? We can. Getting NCO to give us enough disk space for that is going to be a problem. But with those longer training periods, you also have, you could be reaching back too far. If you're in summer and you reach back 6 months, you're going to be in winter. So there's always the battle there. The trade-off between sample size and what is relevant to the current, to the current forecast.
Okay. Yeah. Thanks. Really interesting. Hopefully, if I can get a copy of your slide set, if you don't mind, that would be awesome.
No problem. Yeah, no problem.
kind of absorb everything. So.
Hey, Eric. This is Bruce in Kansas City. Just a quick question here, and really this is on behalf of all three of us sitting here at the table. And I won't ask the question maybe as eloquently as Randy would have, but the part that blew my mind a little bit here was the introduction of the random number generator in there. And I wonder if you could just explain again in sort of layman's terms the rationale for that. You know, I think we think of something like this as being a perfectly objective, static sort of a process, yet we're throwing that randomness into it. So what does that accomplish, and what was the rationale for adding that into the process?
Yep. And admittedly, in Tom's journal articles and just in general communication, that this is the current method of dressing is not ideal. You know, we always have the battle of you can do something really special with a 3-month, you know, training period, but when you have to apply this in production and run things over and over, you can't necessarily do some of the you know, for lack of a better term, cooler methods of dressing. So, you know, after you quantile map, there's still some information there that can be extracted to further correct, and also the fact that sometimes when you look at your collection of quantile mapped forecast values, there could still be some lack of spread. So the addition of noise to each quantile mapped forecast value hopefully helps with the spread of the collection of your ensemble, essentially your huge multi-model ensemble. Helping with spread will help with, you know, hopefully with reliability. So that's kind of the motivation there. We would really like to, you know, in the second journal article listed, there is Tom Hamill's latest paper from 2018, where we get the gamma CDF idea from. There's also another aspect to that updated procedure, which is called, make sure I get it right because I'm going off the top of my head. It's called rank weighted best member dressing, and you know that's probably a 2-hour, you know, PowerPoint in and of itself. I would love to get that implemented for 4.0. We might run into you know, disk issues with that because that requires now archiving your quantile mapped values. So, you know, archiving 1,500 forecast values at every 2.5 kilometers at every lead time. So that's kind of the point of the dressing, is to, you know, help with the spread for the probabilistic output.
Great, thank you, Eric.
Any other questions out there? Not seeing any. Do you have anything, Randy, otherwise?
No.
All right, well, Eric, thank you for taking the time of your day to present this to us. Much appreciated. And yeah, like Phil said, if you want to share that with me, and then I can send it out to all the Sues here in CR.
Okay, that sounds good.